Yeah, cool bio.
All right, I think we're ready to go. So yeah, I'll turn it over to Elisa to introduce our speaker today. Well
Okay, great.
prepared.
Well prepared, me. Yeah, I am
Oh, you
gonna.
went on an internet bio. Oh, no.
No, this is, I might read the bio because it's very interesting. Yeah, so today we are very fortunate to have met Clement come give us a talk. He's a well-known dynamicist and solar system and exoplanet scientist. So a couple things to note from his bio. During his postdoc work at Carnegie, he used numerical modeling tools to study the formation of the solar system, focusing on the terrestrial planets and how they're informed by geophysical and cosmochemical constraints. Before starting grad school, Dr. Clement spent 5 years on active duty in the Navy, where he was stationed on the nuclear-powered fast-attack submarine USS Topeka, first as the ship's chemistry and radiological controls officer, and later as assistant engineer. As a qualified Navy scuba diver, he was also the ship's diving division officer. And so he has a very interesting and varied background and is going to talk today about Mercury's formation.
Yeah, thank you so much. Great to be here. You guys are always welcome at APL. We're just down the road. But yeah, sometimes it seems like a million miles away, even though we're all right here. Yeah, why did I want to talk about Mercury? Well, I had these slides together that helped. But also, yeah. There we go. Also, yeah, I think Mercury lies at the interesting intersection of a bunch of different fields with a bunch of different open questions. This is not for this web I've made here is not to like go through in gory detail or to have everyone read all of this, but it's just to kind of illustrate the point that there are a lot of the biggest outstanding, well, not outstanding, but biggest, mysteries regarding why the solar system is so different than exoplanets, can kind of be summed up in Mercury and what is interior to Mercury or the lack thereof. How that happened in the solar system, that we didn't end up with a system of short period super Earths and instead ended up with like the farthest thing from a Mercury. Mercury is also the most differentest planet in the solar system for many reasons. It's different from the other terrestrial planets in that it's just a big hunk of iron with a very tiny layer of mantle and crust, whereas Earth and Mars and presumably Venus have cores of like 30-20-ish% their total mass and much larger silicate mantle. How did that happen? Mercury is also much smaller than the other terrestrial planets. It's also on a much more eccentric and inclined orbit. So from a dynamical standpoint, a formation standpoint, a geophysics standpoint, it's drier than Earth, obviously. It's made out of different stuff. It really is a nice little if we could figure out what's going on with Mercury, we'd be able to answer a lot of things about a lot of different fields. And spoiler alert, I have not figured out what's going on with Mercury in spite of writing a lot of papers about Mercury, particularly as a postdoc. I will probably end this talk with more questions marks than are even on this page. So the way I structured this talk is I'm going to kind of hit on all three of these main nexi in this slide here. I'll start talking about Mercury and its connection with exoplanets, and I'll talk about Mercury and its connection with kind of solar system cosmochemistry, in particular what's going on with its internal structure, and then talk about kind of trying to build a working formation model for the solar system that includes Mercury, which is definitely an outstanding problem. So I'm going to come back to this slide again, but just, so I'm going to talk about these things over and over again in this slide, just some numbers to put up on the slide so everyone remembers them and they're fresh in mind. What's so unique about Mercury in the context of the solar system and of multi-planet, systems of exoplanets is not just its mass, Mercury's mass is only a few times that of the moon. It's like 5% that of the Earth. Its mass ratio with respect to the planet closest to it, Venus. Mercury is 15 times, or Venus is 15 times larger than Mercury. When we find systems of multiple planets, they tend to have similar masses and radii. This is definitely not true in the solar system's terrestrial planets, particularly the most extreme planet pair is Mercury and Venus. And this we'll get to later. This does not come out of formation models at all. You form something where Mercury is, if it forms in conjunction with Venus, their formation is almost coupled, which is not the way they are in the modern solar system. They tend to end up with similar masses, just like Venus and Earth. And our formation models work for Venus and Earth, so we don't want to like completely throw them out. It's also kind of the most dynamically isolated planet in the solar system. So again, similar with when we do demographic studies of exoplanets, we don't necessarily care about the actual semi-major axis of Mercury. What's more important dynamically is its orbital period ratio with respect to the neighboring systems of planets. And this is the most extreme in the solar system as well. Like the orbital period ratio between Earth and Venus is like 1.7. This is very common for exoplanets. The majority of exoplanets that are not in like the scattering population, we find with orbital period ratios between like 1.5 and 2. This is how things like to form too. This is kind of a stable zone to be in. And Mercury is well outside of that. And as I mentioned, it has this funky for a terrestrial planet internal structure where it's this huge ball of iron with this tiny little thin skin of mantle. And it's also on the most dynamically excited orbit in the solar system. All the other planets in the solar system, to include the giant planets, have inclinations within about 2 degrees of one another. Even the mutual inclination between Jupiter and Saturn is only like 0.5 degrees. That's small, even compared to giant exoplanets. The solar system is very coplanar. It's very regularly behaved. Mercury is not. There's a large eccentricity as well. So the first thing I mentioned as far as why Mercury is weird and why the solar system is weird is that lots of sun-like stars have this population of super Earths and sub-Neptunes very, very close to the central star. And we do not. And as I said, we have the opposite of that. We have a Mercury. So what is going on here? To understand what is going on here, we have to understand a little bit about how planets formed and how we think all those different populations of exoplanets formed. This is probably a review for a lot of people, but I'll go through it kind of quickly. Stole this plot from Sean Raymond. This is a great series of slides you might have seen before. So if you have, I'm sorry, but I added a few animations on top of this to make it my own a little bit. So all the action, the majority of the action of planet formation takes place in the first few million years, while the gas disk is still around. We have kind of good constraints on how long the gas disk was around in the solar system and other systems, from looking at globular clusters, and as they get older and older by their velocity dispersions, you get fewer and fewer infrared excess sources, fewer and fewer protoplanetary disks. We also have lots of constraints, geochemical constraints in the solar system, of from meteorites, when things formed, and what the environment that they formed in was. So we know fairly confidently that the gas disk in the solar system only was around for kind of our best estimates are like 2 to 3 years. So by extension, we have to go from time zero from a newly formed star and a disk of about 100 times as much gas per mass as dust to up like 30 orders of magnitude in mass, all the way to the mass of Jupiter. And that has to, that asymptotically has to happen in this window to, dump all this hydrogen and helium into Jupiter. So, people do studies of, computer simulations and laboratory simulations where they try and replicate, the kind of relevant conditions of, dust particles slamming into one another. And this works up to a point. You can grow, these dust aggregates of millimeter to approaching centimeter scale fairly efficiently, fairly quickly, and then you run up against some barriers. It's these aggregates get long enough, they're not like, these are not like dense, compact, solid things. These are big kind of clumps of dust, and eventually when they hit each other, they tend to fragment. So there's this dust fragmentation barrier that you have to overcome. And then the more important barrier is that as things grow by slamming together in the protoplanetary disk, they start to interact with the gas. They start to decouple from the gas, which is orbiting at a subkeplerinian speed, and that these growing dust chains into little pebbles are orbiting, at a Keplerian velocity, so they feel the gas headwind effectively, and they feel this drag force, which causes them to spiral into the central star. This has been known as a major problem in planetary science since the 70s, and it turns out that the worst size to be orbiting, in a gas disk is about a meter or so. That's where you have the fastest spiral inward towards the central star. So even if you're able to overcome that fragmentation barrier and get up to meter sizes, once you reach a meter or so, you spiral into the central star within literally like, dozens of orbits, hundreds of years. So these are two of the biggest, problems in planet formation over the last 50 years. There's obviously there's multiple potential resolutions to this. This is the kind of going consensus model now, is called the streaming instability. There are many problems still with the streaming instability, but the streaming instability basically proposes and has proven out through simulations and through predictions. One of the biggest predictions being forming planetesimals in binaries preferentially, and then discovering contact binaries out in the Kuiper belt. So there's been a lot of empirical evidence for this, but basically what it proposes is that you can concentrate dust particles in regions of the disk in kind of a it is sort of a process that's like a feedback loop effectively, such that you can eventually reach the threshold for direct gravitational collapse, and you can do this very quickly. And the reason for this is, if you have the slightest kind of under or over density within the protoplanetary disk, a region that's over dense of dust particles, that now it couples more strongly with the gas, orbits, it drifts inward slower relative to the other stuff, causing more stuff to dump into that region, causing it to get denser and denser and denser, and eventually gravitationally collapse. And this process can form planetesimals of order tens to thousands of kilometers. Another good kind of smoking gun that this is goes in the right direction is the sizes of the planetesimals that are formed in these simulations, like what's being shown here, which people run these kind of one-dimensional particle in a box simulations, where you're basically looking at, a one-dimensional box, or I guess two-dimensional, sorry, box down, looking down in the protoplanetary disk that's rotating at the local Keplerian velocity. So stuff that you see moving back is rotating sub-Keplerian, forward is rotating Keplerian. And you're able to form, these white points, what it's showing here, and it's labeling them with the approximate size in kilometers of these planetesimals that you're forming. So that's how we get to planetesimals, and then things start to bifurcate depending where you are in the disk. So if you're closer to the central star, you are that the local temperature is hotter. So the population of planetesimals that are forming are rockier, less icy, because all of the ice is in the gaseous form. You can continue to grow in this region if you form rocky planetesimals by the obvious way of slamming into other planetesimals. People have done these types of simulations, like what's being shown here is just literally put a whole bunch of planetesimals down of, sizes of 100 kilometers or so, with kind of total mass that adds up to the Earth, kind of near where the Earth is, and in, hundreds of thousands to millions of years within the life of the gas disk, you can continue to grow by this process to, not necessarily the mass of the Earth, but definitely the mass of Mars. You can also grow via pebble accretion. So, as we mentioned, you're orbiting in the gas disk at a Keplerian velocity. You're big enough to kind of have surpassed that meter barrier, so you're not spiraling into the star super fast. There is still this kind of flux of junk that is spiraling into the central star. So it's much easier to accrete a tiny little, centimeter size, millimeter size pebble, as what's being, shown in this video, because the range at which, you're going to gravitationally deflect that thing versus the range at which that you're going to accrete that thing is much different. So it's much easier for growing planetesimals to accrete pebbles than it is to accrete other planetesimals. We also don't know how strong the pebble flux is in the inner solar system. There's lots of reasons to think that it was not particularly strong. First of all, pebbles that form out in the outer solar system that are inherently very, very icy, because it's very, very easy to form large icy pebbles out where it's very, very cold. They're going to evaporate as they move on in. Also, at some point, this process was probably stopped or completely hindered, at least in the solar system, because of the formation of Jupiter's core. Once Jupiter got large enough, it was going to kind of suck up all the incoming pebbles and block them from the inner solar system. But as I said, you can kind of form, Moon to Mars mass embryos within the life of the gas disk, which is depicted here by that, fading away, kind of gray color there. And then if you kind of take that bimodal population of embryos and planetesimals that comes out of that process and put them again in an in-body simulation, this is the type of simulation that people have been doing since the 90s. It will, things will continue to combine and accrete, and in hundreds of millions of years or so, you can kind of reach a stasis where you've cleared out the majority of the planetesimals from the planet forming region, and you end up with like these Earth mass planets. And this model does a very good job. It's been around for a long time of forming, Earth and Venus mass planets kind of where they should be. This is kind of a classic simulation with classic initial conditions of the solar system, where you're able to take just this minimum mass solar nebula, mass distribution, and clear out a bunch of the asteroid belt and end up with 4 planets where they should be. There's some problems with this model too, but if you scale up the mass too, you can also, the total mass of the planets before and after are very similar in this model. This is a very, very efficient process, whereas pebble accretion could be thought of as inefficient in the sense that a lot of the total mass available to form planets does not form planets. It gets dumped onto the central star. But if you form things by a planetesimal accretion, you don't lose a whole lot of the planetesimals in the process. So if you just, start with 5 times as many planetesimals in the same area, you can form super Earths, within the same similar amounts of time. So this works as well. Outside of the snow line, further from the star, pebble accretion, as I mentioned, is much more efficient. As I said, the pebbles are larger. There's more of them. It's easy to form these big icy pebbles. They're not evaporating away before they can, get accreted onto a core. So we can form, very, very large cores very, very quickly via pebble accretion, of order the inferred core sizes of the giant planets. So of order, 10 to 50 Earth masses or so. And then once you kind of get beyond a few Earth masses in size at, kind of the 5 to 50 AU region, you get back into a mass range where migration is very efficient and things can start to migrate around as well. And if you're able to stick around, kind of close to or far from the star where there's a lot of gas to suck up and not migrate in too far, you can get large enough, and then you can reach kind of the threshold for runaway gas accretion, and we can form giant planets. So where do all the short period super Earths come from? Well, there's multiple models out there. I'm just going to show one of them, but what, kind of the Goldilocks model would be to sort of get, all these different types of planetary systems to form in one single model. So what might make the solar system different than systems of super Earths is kind of being shown in this movie here. Is, you efficiently form these large cores far from the central star, several AU and beyond. In the solar system, Jupiter just forms so fast, so large, that it kind of, stayed where it was, or relatively stayed where it was, and, stayed far from the star and underwent runaway gas accretion, and then kind of stopped the inward pebble flux from the inner solar system, and kind of mass deprive the inner solar system, but that's not always necessarily the case. In a lot of systems, we would think, pebble accretion is not necessarily that efficient, out where Jupiter is, and things kind of stall out before they can reach that threshold for runaway gas accretion, and they start to migrate in, and they stack up and form these, chains of super Earth sub-Neptunes, very close to the central star. And as I mentioned, we have, not just the empirical evidence that we don't have super Earths as evidence that this didn't happen in the solar system, but we also have evidence from meteorites, where we have these very, very complicated, compositionally segregated meteorite groups in the solar system, the non-carbonaceous and the carbonaceous chondrites, which formed at different times in different places. And this fits in well with a model where at some point, Jupiter got large enough to physically and chemically segregate the early solar system. So there's lots of evidence that we, at least didn't form super Earths in this manner. But hey, what if we did? People have proposed this. This is not the only paper out there that goes along this idea. It does, as I mentioned, it does. There are lots of mysteries surrounding Mercury, not just that Mercury isn't a super Earth, but Mercury is weird for lots of reasons. So it, doesn't take a large stretch of the imagination to propose, like, well, maybe if there was a primordial chain of super Earths that was lost, maybe that could, you could explain some of those other things about Mercury. Maybe it survived as this iron only fragment. Maybe that's why it's so far from Venus. So people have looked into this. This is a plot here that's, kind of showing quasi-stability in a known exoplanet system, just because we observe planets doesn't necessarily mean that they're stable. The solar system, is stable, but it's chaotic in the sense that it could go unstable in the future. So planetary systems don't necessarily have to be stable, when we see them or when they form or at any point in their lives. So I show this to say that it's out there, but there are lots and lots of problems with this. It has never been able to be developed into a model that can account for where all the mass and debris goes. I'm going to talk about that in a little bit later when I talk about some of the models for Mercury's formation. If you cataclysmically destroy a chain of short period super Earths in the solar system, the mass has to go somewhere. Presumably it has to go onto the sun, which is hard to do at different times in the solar system's life. Dust wants to go, out instead of in, or wants to stay where it is. So you have to do this. You have to not disturb the orbits of the known terrestrial planets. As I said, everything except for Mercury is on a very, very, nice circular orbit. And the cataclysmic event like this is surely going to perturb those other orbits, and also dump a bunch of material onto Earth and Venus, presumably, after the protoplanetary disk went away. And we have lots and lots of constraints, particularly the last, 100 million years or so, from like, the late veneer of Earth, for example, models of Venus's internal structure that, kind of strongly preclude dumping a lot of mass and dumping a lot of dust onto Earth and Venus late. So in conclusion, I don't think we ever had a system of super Earths in the solar system. Doesn't mean we couldn't have, but I think there's other, perfectly functional explanations for why we went down a different formation route than systems of super Earths, and more on this later. So moving on to Mercury's core and the reasons why Mercury looks so much different physically than the other terrestrial planets. So the canonical explanation for this is Mercury got hit by something. You might have seen some of these models before, or reference it in the literature. This is the most well-known explanation for Mercury's odd core mass fraction, but it's certainly not the only one. If you do this by an impact, there's kind of two options here. Mercury is either the bigger thing or it is the smaller thing. So on the left here, this is kind of the classic model. It's been around since the 80s, where Mercury is, about twice the size it is now, roughly chondritic composition, and core mass fraction of similar to the Earth, and it gets hit by something a couple times the mass of the moon at a fairly direct angle at a very, very high velocity in an SPH simulation. When you set up the right kind of impact, you can, grind a whole bunch of the initial two planets to dust and end up with, given the appropriate, initial geometry, end up with a nice Mercury analog that has a nice core mass fraction and fits a lot of the other, parameters that we have for Mercury. The other option is Mercury is the smaller thing. It, has a hit and run impact effectively with a bigger growing planet. Presumably this has to be Venus or Earth. You can do this at a slightly slower velocity, still a pretty extreme velocity, and still has to be to do this in one impact. We're talking a little bit about doing this with multiple successive impacts. Still has to be a fairly, head-on collision. So the biggest problem with this, it's a known problem. People have been complaining about this for, since, way back in the literature, is again, what happens to the ejected material? It has to go somewhere. So there's multiple solutions out there to this in the literature. I'm not gonna, say any of these are wrong, just that, some of these have to work at very specific times. So there's a model out there that you can get rid of a lot of this dust from this impact if the solar wind is a little stronger than we think it might have been. But at some point, this as the sun kind of evolves as it hits the main sequence, at some point you're more likely to push stuff away from Mercury than you are to push it onto the sun. You run into these problems with dumping that mass onto Earth and Venus again. There's models out there for doing a Poynting-Robinson drag, Minkowski drift, if the objects, the characteristic size of the debris is large enough. But again, you run up against all these other constraints from the other terrestrial planets by shoving around a whole bunch of mass in the inner solar system too late. So again, I'm not going to say any of these can't work, but I am going to say that there's other very, very inherent dynamical problems with this model. So at first glance, if you want to get a very, very energetic collision, where Mercury is not a bad point in the solar system to do it. So this very, very funky looking plot here, what this is showing is if you take Mercury, which is the red star, probably bad color choice there, but I circled it. You take it and you just move it around in inclination, semi-major axis space. Its orbital evolution varies drastically. So what's being plotted here is just the, kind of half the change in the eccentricity. So as this eccentricity is changing, by like 0.5, basically, that's a very, very unstable orbit. It's going to eventually, slam into one of the other terrestrial planets or get ejected from the system. So the yellow regions, the red regions are more stable regions. And the Mercury, where it is today, sits just right on top of a little island of quasi-stability, which is kind of sandwiched in between the new 5 secular resonance with Jupiter's eccentricity precession, the 3-to-1 mean motion resonance with Venus, and a bunch of secular resonances with Venus, the new 1-2 and the new 2 secular resonance. So it's a very, very dynamically rich chunk of the solar system. And what you need to get the right impact, to get that, 30 to 60 kilometer per second impact velocity that these models prefer, you need some pretty crazy orbits. And that my point is that this region of the solar system can produce these orbits. So this is just a plot showing like which orbits for those two different models, Mercury as the target or Mercury as the projectile, which orbits in eccentricity, inclination space are going to, give you an impact where Mercury is at that appropriate collisional velocity. So you can produce those if you start junk in that very, very dynamically complex region where Mercury is today. The problem with this is from a 2019 paper where we put a bunch of stuff in these unstable regions, and we got a bunch of the right type of collisions in terms of head-on impact, right collisional velocity. The problem with this is that it massively overexcites the orbits of Earth, Venus, and Mars. What's being shown here is the angular momentum deficit, which is a nice proxy for orbital excitation of Earth, Venus, and Mars after several of these different, scenarios that we picked, where we put objects at different, at different spots on this graph and let them collide. And, only 5% of the time or so do you not drastically overexcite the orbits of the other terrestrial planets, which the solar system value for the AMD is the red line here. So doing this, massive energetic collision without disturbing the other terrestrial planets is a problem. It's particularly a problem for, Venus or Earth being the impactor, because the action is happening right where they are, and it's easy to overexcite them. So the best way around this would be for the action to happen very, very far, or as far as possible, from Earth, Venus, and Mars. In the interest of time, I'm not going to talk about this plot on the left too much, but it's to illustrate the fact that it's very easy to excite orbits in the very, very inner solar system near where Mercury is. And you need it to happen far from Earth and Venus and not involve them at all. And it helps too to be able to do this via multiple impacts. So this is a kind of toy model we set up where we just set, 5 or so Mercury to Mars mass embryos inside of the fully formed Earth and Venus. And you're seeing these little green dots spit out, those are collisional fragments. These things are inherently unstable. And what you can do is you can, you routinely get instabilities if, all the action is happening between smaller objects far from Earth and Venus. And you can get fragmentation events. So this is plotting the final core mass fractions of the objects, different models that we picked. So the core mass fraction that they start with is 0.3. So lots of the time you're able to end up with a final Mercury with a large core mass fraction, just like the SPH models predict. But more importantly, half the time or so, you're able to do this without overexciting the angular momentum deficit, overexciting the orbits of Earth and Venus, which is being showed in the middle plot. And you do it by all sorts of funky encounters. The plot here on the right is showing one such example where Earth and Venus's orbits, the blue and the yellow lines there at the top showing the perihelion and aphelion of both of the planets don't get affected too much. And you have Mercury's core mass fraction is altered in a bazillion different, impacts between all these different fragments that get shot out, which is all the different colored lines. And you finally end up with this, good Mercury at the end. Again, the types of impacts that we see in this model, they work. They're consistent with the SPH literature, which is being shown here. The different shapes are different kind of preferred models from different formation models for Mercury. So it works to do this all there. But, I want to emphasize that this is a toy model. This is not something that comes out of a planet formation model or protoplanetary disk model where you just happen to have these few little Mercury stranded there to have this chain of impacts to give you Mercury. It works, but we should not discount the fact that there are plenty of other explanations for Mercury's core mass fraction, some of which tie in with exoplanets that are potentially as well developed as the impact hypothesis, but certainly not as well referenced and known, I'd say, in the field. The first one I'll talk about, and I'll just talk about these very briefly because this is it's literature that us modelers get to cherry pick from as we choose, and I'm not necessarily the expert on any of this stuff, but people have proposed so all these models hinge on forming two types of planetesimals in the inner solar system, one of which is more iron rich and one of which is more silicate rich, and then presumably the more iron rich planetesimals form Mercury and the other ones form the other terrestrial planets. So the photophoretic effect, people have shown that if you have non-isotropic radiation bearing down on the dust to millimeter sized particles, you can kind of size sort them. So if you have preferentially form these larger silicate aggregates than the metal aggregates, you could size sort the region and then compositionally sort the region. There have been a bunch of follow-up papers on this as well. A kind of similar idea. Again, if you have these long iron aggregates, if the magnetic field in the young solar system is just a little bit stronger than we think it might have been, again, you can size sort these objects. You can size sort the iron stuff and preferentially form large iron rich Mercury precursor planetesimals. There's also a recent paper by Johansson and Dorn from 2022, where they tried to make the argument that iron has a higher surface tension relative to silicate, so that's going to cause iron particles in a super saturated environment to nucleate inhomogeneously relative to the silicate particles. And they were trying to use this more to explain super Mercuries, as being shown by this plot here, but it certainly is applicable to the solar system as well. They make that case in the paper too. There's these laboratory experiments from the Evelyn Alexander 2011 paper where they took pre-solar interplanetary dust particles in a very, very carbon-rich environment. They were able to produce these condensates that were approaching the bulk iron silicate ratio of Mercury. So, if you had this carbon-rich environment where the Mercury precursor planetesimals were forming, you could potentially explain some of this. So, we'll talk about this a little bit more later, but in conclusion, I don't like the Mercury striking Venus or Earth to get this nice hit and run collision that somehow forms Mercury and then somehow strands it back on that orbit that's super detached from the other terrestrial planets. There's no good way out there to get rid of the ejecta, not have it dump onto Earth and Venus. There's no good way out there to recirculate its orbit. So if it is an impact, we like smaller objects. We like multiple impacts, doing this by like multiple hit and runs. It's much more likely than just the one perfect head-on collision that just does it all perfectly in one collision. Those things are extremely rare in planet formation simulations. And but yeah, we should not discount all these other models, particularly in the geochemical literature, that and the connections with exoplanets as well, that there might be other ways out there to preferentially form planets close to the star that have boosted iron contents. This would be a great way for like exoplanet demographics in the future to be able to weigh in on and break the degeneracies between these two problems, right? If you preferentially tend to always find boosted iron content planets, super dense planets, close to the star than further from the star, this might say something about what happened with Mercury. So finally, in the last third of the talk, we'll talk about my research. I guess I talked about it a little bit, but yeah, what I do is I run these plant formation models. I had a whole bunch of compute time as a postdoc, and then COVID happened, so I had nothing to do. So I just threw a whole bunch of stuff against the wall to see what would stick with Mercury, and not that much did. But we think I'll kind of conclude with a somewhat working model that we're continuing to develop now. So again, going back to what our main constraints are in our planet formation models, we want Mercury to be very, very small relative to Venus, very, very far from Venus. If we're using a code that can kind of track the internal structures of these planets, we want to replicate that core mass fraction, and we want it to be on that dynamically excited orbit, although this is not necessarily a huge problem, for multiple reasons. As I mentioned, this is a very, chaotic region of the solar system. There are other ways to excite Mercury's region, Mercury. So as a caveat, I'm going to show a whole bunch of stuff, different models from the past literature. I'm not trying to say, people didn't know what they were doing and they weren't trying to form Mercury. It's really, really hard to do this. Mercury, to resolve, in mass and in dynamics, the whole inner solar system formation problem. You run up against resolution issues because Mercury is so much smaller, so you need a whole bunch of particles to be able to form Mercury. But if you're gonna have that many particles all the way out through the asteroid belt, your problem becomes computationally intractable. And also, if you want to resolve the orbits of Earth and Mars for hundreds of million years, and also Mercury, which is much closer, you need to use a smaller time steps. These things are hard to do. So it wasn't until recently that we could kind of, make these studies computationally feasible. But I'll compare here first to, I already showed this video, what's kind of considered the classic model of terrestrial planet formation. We just have this smooth radial distribution of material going all the way out to just, inside of Jupiter's orbits. This has a well-documented small Mars problem. You've probably heard of some of these models in the literature. You tend to form like the largest planet, as seen in this video, is out where Mars is. We have a whole bunch of solutions to this. It has a less documented and less well-known small Mercury problem. So I'm going to continue to overlay more points on this plot, but what I'm plotting here is all Mercury analogs that come out of a set of simulations. This last one was 100 simulations that we did with these sorts of initial conditions. All the Mercury Venus systems that come out of them. So it's just like every time you end up with exactly 2 planets inside of like 0.85 AU, that's a Mercury Venus system. What's the ratio of their masses? What's the ratio of their orbital period ratio of their orbital periods? And how does that compare to the red star, which is the actual Mercury Venus system? So this classic model, as I said, you do not form small Mercuries. Oftentimes you form, your Mercury Venus system is Mercury more massive than Venus. And oftentimes too, because they kind of have to truncate the inner disk to make the problem computationally feasible, oftentimes you just end up with one planet there. So the first thing I talked about, that might be the good explanation for what's going on here, is collisional fragmentation. So, we took the exact same problem, exact same initial conditions, and instead we used a newer code that accounts for collisional fragmentation to see if maybe you preferentially grind that stuff down more closer to Mercury, and you're able to kick out a small fragment that'll become Mercury, a la these nice, impact models in the literature. And so one of the first things you should notice in this video is that, you see more little dots bouncing around for longer. That's the biggest difference when you account for fragmentation in these planet formation models. You are continuously re-injecting, a planetesimal population, which is these collisional fragments. And yeah, this system here, you do occasionally through this process, kick out some fragments that are able to form this small, approaching Mercury's mass, Mercury analog interior to Venus. The problem with this though is that, it's a resolution problem to try and, get down to Mercury's actual mass, but we still weren't able to produce Mercury's actual mass consistently here. But we definitely were not able to, replicate that orbital period ratio. Something weird is going on there, and I'll get to that in a little bit. It is, these fragments that get kicked out, they're either, remain dynamically coupled to Venus and that they can't get kicked out in this orbit that's so isolated, or if they have to be kicked out on a geometry that's with a velocity that's sufficient to decouple them, they're very likely then to have these large eccentricities where they get scattered around further and then end up colliding with the sun or ejected from the system. So one of the kind of preferred models you see out there in the literature now for both the solar system and for exoplanets are these so-called annulus models. These fit nicely with planetesimal formation models that argue that you're tend to form planetesimals at these narrow annuli in the disk, which is why you end up with planetesimals that form with very similar compositions. They form at a certain time at a certain place in the disk. This model also works really well for forming small Mars because you kind of scatter Mars out of that little annulus, and it can work forming a small Mercury as well. You can kind of see there's a poorly colored pink little fragment there right inside of Mercury's orbit. So now we're starting to fill this plot out a little bit more. Now what do we have here? The blue, green, and green points are from various studies in the literature and from my own using these annulus models. And you see we're now able to eject these small little planetesimals from the narrow annulus. So you can replicate Mercury's mass, but again, it's very, very hard to strand something so far out there and replicate the period ratio. And what's going on there? I think it has something to do with the giant planets in the solar system. Again, this plot here on the left showing the dynamical complex region around Mercury's orbit. The biggest thing that drives chaos, this orbital chaos near Mercury's orbit, is the secular resonance with Jupiter, which was not always where it is today. When the solar system went through its giant planet instability, what's being shown here in this video, this resonance would have been much further out in the terrestrial system, like closer to where Mars is, because Jupiter and Saturn were much closer to one another, so their mutual forcing on one another was larger, and as their orbits diverged, the resonance would have moved in towards where Mercury is. So the consequence of all these resonances sweeping across the inner solar system, it can efficiently deplete the Mars region, so it helps you form a small Mars, but it can also give you that sweeping to occasionally grab hold of a little would-be Mercury from somewhere else in the disk and kick it all the way out there. And you see now, so we've layered the pink points on here. And in some of these models, we are now, able to replicate that orbital period spacing, although it is still rare. Talk about this one really quickly. You might think, okay, like, well, what if you just had some kind of funky mass distribution? Can we get that to work? People have tried that. I've tried it too. I'll show in a couple slides. These are the yellow points here. Very hard to get that to work as well. And then returning to the toy model that we set up here, how do these points plot on this plot, where we try and get the right impact to work? These are now all the other points I've shown so far are gray, and now the new ones from all our simulations that formed good Mercury core mass fractions and Mercury masses and didn't overexcite the terrestrial planets. Wow, they fall all the way on the wrong side of the red star. So this is another big problem with this model. Like, if you have the action, as I talked about, if the action happens far away from Earth and Venus, the stuff that tends to survives in that stable region of the inner solar system, far away from that bad resonance with Jupiter. And so you overshoot that orbital period ratio, and all the stuff, all the fragments and all the junk that are on the Mercury side of that resonance with Jupiter all ends up colliding with Venus and Earth. So now hopefully you're like totally confused and you're wondering if this talk's ever going to go anywhere. So in the final few slides, I'll kind of leave off with where I'm at now, where I would think, might be a close to hopefully soon working model. So we went back to that idea I alluded to earlier. We're like, let's just play with all the different parameters. Let's be like a full theorist and just tune all the knobs and see what can work. So we adjusted not just the surface density profile interior to Venus, but also its mass distribution. How much planetesimal mass versus how much embryo mass you have, how much total mass you have. We just completely tuned all the models, and we were able to get a few, like this video here, where we had a few of these blue stars. Now, again, the blue stars are the new set of simulations compared to all the past stuff in the literature, where we were able to get everything right. Our best set of like 10 simulations, we had 4 that all like matched all our constraints, and are 4 of those, you know, good points up there at the top. So, okay, so what worked? You needed a shallow surface density profile. So you needed like a depleted region of mass interior to Venus, there where it was this kind of extensive distribution of not a whole lot of surface density that went, you know, all the way inwards towards the sun. You needed a whole lot of planetesimal mass, which is problematic too, because you need all that additional mass to kind of stabilize the orbit of Mercury as it forms and prevent it from colliding with Venus. So, okay, great, Matt. Like, where does that come from? How did you possibly get this published? What are you doing here? So how might we motivate this disk? Well, we thought about that for a little bit, and we went back to the only like 2 tools that we have in, you know, dynamical studies of planet formation: migration and instability. It's like the 2 resculpting mechanisms we have to play with. So we just decided to play with migration. As I said, depending on the disk, you know, structure, things start to migrate around, and they can migrate inward or outward. This plot shown here is showing these different contours of inward, outward, and null migration, the black, blue, and the red at different points in the disk for a relatively small object, as small as like, you know, an Earth mass or so. And if you play with some of the other disk parameters, you can get this down even further to like half an Earth mass or so, where you can start to migrate. If you can reach half an Earth mass, you can start to migrate around somewhat substantially within the life of the gas disk. Not the only ones that have played with this sort of model, other people have as well. But, you know, this is showing stuff that I did, but there's other stuff out there in the literature too, some of which is being plotted here. There's more recent stuff since this plot. People who do high resolution simulations of planetesimal formation and evolution in the gas disk very early on have shown that, like, close to the central star, you can reach by just planetesimal collisions, you can reach about a half Earth mass within the life of the gas disk, where you could start to migrate around. So one more little wrinkle to further motivate this. I swear I'm going somewhere with this. The Earth is also compositionally distinct from Mars, and this is an ongoing problem. You know, I'm going to show a potential solution to this here, but this is a huge outstanding problem, because in all these models, all the different stuff I just showed, all the different points I put on the plot, Earth and Mars, you know, form out of the same stuff. They're really close to one another. They want to form out of the same stuff. But, you know, from Martian meteorites, we think that Mars, its chondritic makeup is like a 50-50 split of ordinary chondrites and instapack chondrites, and Earth is more like 70-30. So what does this have to do with Mercury? Well, let me show you. What if Earth and Venus formed closer to the sun than they are now? They formed more where Mercury is, in a, you know, closer to the sun, drier reservoir of enstatite chondrites, whereas Mars started forming a little further out in the disk in the ordinary chondrite reservoir. And then once they got big enough, they migrated outward, as we showed. If this happens, you know, they get big enough later on, then you can get these contours of outward migration. So that migrates them through this whole planetesimal region. They accrete stuff and they scatter stuff around as they grow. And so that mass depletes that region, and it gives you this strange, you know, planetesimal rich, shallow surface density profile that I talked about. And you can match a lot of constraints. So I'm showing a time evolution of the orbits here on the left, where you strand this Mercury super far out that forms in this like mass depleted reservoir that Earth and Venus migrate through. And then what's being shown on the left here is matching constraints for the planets' bulk compositions, Earth and Mars in red, showing where the other planets end up as well. Venus ends up kind of like Earth. Mercury ends up all over the place. It's all the different lines there, depending where it originated. So Mercury could be quite wet or it could be quite dry. and then match the constraints for all the planets' masses. So this works fairly well. So then we tried to kind of throw it all together in one model that has everything in a whole solar system. You have the giant planets going unstable. You've got, that nice, depleted disk interior to Earth and Venus. And we're able to match a lot of constraints sometimes with this, but this is to illustrate that this is still very hard to do. The solar system is still a very hard problem. We have too many constraints, and it's very hard to match all of them all the time. So again, here in this one, we massively overshoot that Mercury-Venus period ratio. This is a good system that matches all these constraints, but we end up with Mercury way too far in. So I think I'm coming up against the hour, so I'll put my conclusions slide up here. This is still very, very ongoing work on these problems. I do not know what's going on with Mercury. I do not know why we don't have super Earths. I wasted a lot of time on this problem. If you have ideas, please tell me. That's where we are now. So thanks for dedicating the hour to sitting and listening about Mercury. Happy to be here. Thanks.
Awesome, great talk, Matt. So I think we can get one or two questions in quickly. We don't have too much time, but does anyone have any questions? Tom, do you have one?
Yeah. How do you deal with making simulations when I would guess, like, if you can make something like the solar system, I don't know, 1 in a million times, you're probably overproducing the solar system.
Yeah. I mean, like that last simulation, we're starting from the giant planets being in the right configuration to get the right type of instabilities, and we're constraining down to the ones where the giant planets fit. Like, yes, you have to run a ton of simulations because it depends what you want to study too. Like, are you trying to study the inner solar system or the outer solar system or the asteroid belt? And depending what problem you're trying to do, you have to potentially run a whole bunch of models and then down select all the ones that get the other part of the solar system right, and then take all those and have that be your statistical sample. So this is already like a huge down selected thing. And yeah, you're already starting with like the right mass and, inside of Jupiter and a whole bunch of stuff. Yeah, I don't know how, like, I'm able to do this for a living. It's all it's all made up at some point.
So can you just do like your canonical initial disk, turn up the high resolution, run it 1 billion times, and then
Still works every now and then.
and then just like conclude like, okay, if you form a Mercury like X% of time, that's fine. That's mean this makes the model works. And maybe if you run it 1 trillion times, maybe you'll match everything from the solar system.
Yeah, I don't know.
Like, do you think that would?
So the one thing we can confidently say now about the canonical disk is that there was not that much mass in the asteroid belt. I think we have enough constraints now to know that it either died off near the asteroid belt, Jupiter sucked a lot of that stuff up, or something happened in the asteroid belt very, very early on, or else we would see fine structure in the asteroid belt that we don't see today. There would be more mass in the asteroid belt than there is today. The asteroid belt would be less top heavy in its SFD than it is today. So the classic disk is definitely wrong in the asteroid belt. I don't think even 1 trillion times can get that right. Mercury, I think 1 trillion times without having like the migration of the new 5 resonance, without having like the giant planets migrate and that resonance move around. I think even 1 trillion times, you're never gonna strand it out where it is. I think they can't show it yet. They don't have the models to show it, but those things are intricately linked. But yeah, I think everything else though, 1 trillion times, sure, you can get it to work once. Yeah.
All right, I think we'll end with one last question from Eric. Eric, do you want to go ahead?
Yeah, thanks, Eric Lopez online. So I just wanted to follow up a little bit on the supers that are impossible to explain, in any ways that make it, ask you a question, make it even harder. a lot of the ones that we found, they're these things that are super Earth mass on, Mercury-like orbits, but not only do they seem to have, large amounts of rock and iron, they seem to have large amounts of gas. They have, seem to have a few percent to a few tens of percent of their mass in hydrogen gas that was accreted from the disk. And so that says to me there's something different going on. They had to finish their giant impact phase while there was still gas around to accrete, which is very different from the story you're telling us on the solar system. And so I wondered if you have any thoughts on why the timing might be so different in the solar system, where you had major impacts going on for like moon forming impact 100 million years, but we have these things that seem to most of their major mass forming impacts happen while there was still gas to accrete.
Yeah, I don't think that's actually the hardest thing about the solar system to reconcile. And it all just comes back to Jupiter. Like Jupiter stopped that from happening. The accretion was slower close to the sun because the inner solar system was mass deprived. If you had a bunch more mass there, then you could, fairly easily within the life of the gas disk form something big enough to, accrete, a primordial hydrogen helium atmosphere. Or if, Jupiter wasn't there to block the inward migration of like Saturn and Uranus and Neptune's cores, they would have just like moved on in, and, with their like vestigial hydrogen helium atmosphere, and stacked on up close to the central star. So I just think it all comes back to Jupiter. Now the big question then is like, why did Jupiter form so fast? Why didn't it, migrate? There's strong constraints on how far it can migrate inward or outward. Why didn't it, migrate inward or outward very far? Why didn't Saturn get so big so as to like then take us into that scattering regime where Jupiter and Saturn were similar masses and they scatter off each other, they just crush everything? That's the biggest question. Why did Jupiter and Saturn grow the way that they did? And I think it all ties back to that. And I don't think anyone has a good answer to that yet.
Interesting. I wonder, because we do have systems where we have these Neptune size inner planets, but they still have Jupiter analog companions. You think it's something to do with the timing of how quickly Jupiter formed?
Yeah, at the end of the day, yes, because this is the solar system. It's a giant planet configuration is also by no means typical. It's not required for exoplanets to have like the more massive planet, the more massive giant planet be the closer one. Jupiter also formed first, and like pebble accretion and direct gravitational collapse simulations don't necessarily say that you have to form the innermost giant planet so much faster than the outer one. Yeah, I think it all goes back to like Jupiter and Saturn, why one grew so much bigger and so much faster than the other one, and it doesn't seem to be typical for sure.
All right, well, I think we will end it there. So let's thank Matt again for the great talk. And I think Matt might have some time this afternoon if anyone wants to meet outside of the meeting. But yeah, thanks everyone for coming out. Thanks everyone online for coming out, and we'll see you next time. In the meeting here.